We're going to practice writing an expression. So this is going to get a little mathy on Wednesday. So we're going to set up an equation of sorts. And then we're also, I don't know if we'll get to the second one, to be totally honest. It's just, we'll kind of see how the first couple go. And then we're also going to practice manipulating expressions in different equations, because sometimes reactions occur in a series of steps. And so we're going to look at some situations where reactions don't occur perfectly, in one fell swoop or equation. But first one we're going to focus on is the equilibrium expression. Okay, so I'm going to look at all of you people already in here. Look at you guys. You don't have to be in here yet, but I'll look at you. Okay, so here's what we've got. Okay, I'm still presenting. So we've gone over this a little bit, or you guys have talked through. Essentially, reactions have to reach a balancing point. They're at equilibrium, they're happening at the same rate. It's not the same amount of stuff necessarily, but the reaction has equaled itself out to a point where the forwards and backwards are going to be about the same. And so these are reactions that occur in two parts. So I don't know how you took notes before. I'm going to guess with the notebooks out, you guys are writing them down. Wonderful. Okay. So what we're going to look at then is a particle level model of what a reaction looks like. So you're going to have a couple practice questions like this on the practice problem set 1. But this is asking us, and this is like, I'm going to assume, I don't actually know what is on your AP exam. Ask me about AP stats. I can tell you everything on that exam, not so much this one. But I'm going to assume this is a kind of multiple choice style question that you might get, because we're going to pick one of the boxes. What we want to look for is where equilibrium has been reached. So first things first. I'm going to label a couple things here just so we can all see it. This is going to be carbon monoxide, CO. This is going to be H2O here. These little dudes are H2. And this is CO2 right here, just so we have a key for our particles. Okay, first of all, what do we notice? And people at home, you can drop in the chat. People in here, you can say it out loud. What do we notice about the differences in the boxes, first of all? What appears to be different in these boxes? I'll take volunteers to start, because I don't know everybody's name. Yes, Marley, I know your name, actually. Oh, okay. Yeah, so like there's more particles in some of the boxes. So there's no H2 in this one. So this box is going to be at the beginning of the reaction. This is only the reactants, if you notice that. So if the reaction hasn't done anything yet, we don't have any products. We're not at equilibrium because we haven't made anything yet. So we can definitely eliminate that one. The other boxes do start to have some of the products in there. These are our products. All right, so now we have to decide where equilibrium would be reached. So basically the reaction is occurring at the same rate. So we just got to start counting stuff. So here I've got H2 particles. I'm starting to make my products. So the reaction has started to happen. Ooh, get excited. So we've got 2 H2 particles. We've got 2 of the CO2 particles. 2 of the CO2 particles. And we're going to kind of keep doing that. So if we look at each box, I've got 1, 2, 3, 4, 5 H2s here. 2, 3, 4, 5 of them there, CO2s. And I'm just going to compare the boxes, and I want to look for where there's no change, essentially. So between the boxes. So here, I've still got 5 of these H2 guys, and I still have 5 of the CO2 guys. So what that's going to tell me is that equilibrium has been reached. So now there's no more changes occurring. There's an equal rate of the reaction happening forwards and backwards to produce, essentially, in this case, roughly the same amount of stuff. So in terms of answering the question, You've just got to find that point where nothing has changed. So between C and D, there has been no change. So we would say equilibrium was hit at this point, and then as we progressed, there was no more change happening. So we can assume equilibrium has been reached. So that is how you would answer a particle model question. That's what it would look like, not in a graph per se, but at a particle level, where you would reach equilibrium. What questions do we have? Because I'm learning this as we do it together. What questions do we have? People at home, feel free to hit the raise hand button. And I'm probably going to ask you to unmute and tell me because that's just quicker. But people in the room, what questions do we have about this particle model picking the correct option? Yes? Yep. Because you haven't made any product yet. So you have to just, like, the reaction has to start in order to go back and forth. Like, it has to actually start. And then once it's started, there's a little bit of chaos happening kind of back and forth, but it has to get started first. Like, you got to actually make some products. The products might not totally form correctly or hit with the right amount of energy, and then you'll kind of have them bounce back. A lot of times gases and things tend to be the reversible reactions, or solutions. Like if things are in a solution or aqueous, the pieces and parts are bumping around a lot more. So it can't be just because, again, the reaction has to kickstart. So once it's started, then once you start driving in the car, then you can put it in reverse. Anyone at home have questions? Or anyone else in the room? Feel free to raise your hand or you just say it. This is a safe space. Okay. And people at home, feel free to drop in the chat or hit the raise hand button if you're like, lady, slow down. We're all getting to know each other here. Okay, so just like anything in chemistry, the reason I love it is because it's got some math. So what we're it's a mathy science. I'm not a biology person much. In anatomy, you guys dissect stuff. I'm not about that either. Okay, we're gonna write today. We're gonna get used to is writing what's called an equilibrium expression. So when you reach equilibrium, you've got an equal rate of a forwards and backwards reaction. Mathematically, we can do some stuff with that. Some chemists figured out this expression. I don't remember which ones, but that's not important. Okay, so an equilibrium expression, it's always K something. It's always going to be products over reactants. And specifically what we look at, not that simple, specifically what we look at is the concentration of things. And there's a certain notation. So we look at, in order to kind of figure out where equilibrium is happening in terms of like the math, it's like we take the concentrations of each of my products and I'm going to multiply them together. And those brackets mean concentration. I don't know if you guys have done that yet, but brackets around things mean the concentration of that thing, so the molarity. So we could do moles per liter or however something is measured. Now, the only thing we do though, and apparently I did learn this, this is the easiest question you can get on your AP exam. One of your questions will be, they'll give you a reaction and you just have to literally write the expression out appropriately. And that's the easiest point that you can get. I just learned that yesterday. So what we do is we take the amount of the thing. So this is like the chemical compound, that's the thing. This is how many of the thing. And we just raise each of these to that exponent. So however many moles of that thing that we have. And then we just do the same for the reactant side, whatever's going to be on that side. So product of your two compounds, the concentrations of those things, and then raised to how many of those things you've got. And that is what's called writing an equilibrium expression. For now, we just want to get comfortable writing it correctly. And then we're going to actually do some math with it later on in the week. Okay, so the only big bullet point here, this is how you'd write it, same format every time. The only thing that we do though is we don't include pure substances. So we don't include anything that's a pure solid or a pure liquid. Because those things aren't going to change anymore. The concentration of those things won't change anymore as the reaction's kind of shifting forwards and backwards. So like if I have a bunch of gas on the product side, but then a couple of those particles go back to the reactant side, you know, as it's kind of doing its thing, the concentration of that will change throughout the backwards and forwardsness. So gases I want to include and aqueous things I want to include. So only include things that can change. So gases and anything that's aqueous or dissolved. So those things. So basically you're going to ignore, right on the screen, you want to ignore solids and liquids. And we're going to do a couple examples of writing the expression. So then if I knew that K is going to have a number value. So like eventually we'll have a number and we'll have to explain to somebody what the number means of our ratio of our products and our reactants. Because it'll tell us in the end, like, you know, which side of the reaction is kind of favored and what that means. Any questions on this part? Any questions from at home? Feel free to put it in the chat. Hopefully I haven't confused anybody too much yet. How are you guys feeling here so far? Okay, and I am recording all of this babbling, so okay. So let's there's only one exception to this. And I'll be honest, I haven't quite remembered entirely when this comes up. But occasionally you might be asked for the Kp value. So this is the K is the constant, the equilibrium expression. It's like K is your constant for your equilibrium expression. Sometimes, I should add this, sometimes this expression gets Kc, C for concentration. These are concentrations. It might also get like Keq. That's another common symbol for it. Just saying like, what is the rate of your products over your reactants at equilibrium? The other option is when you've got all gases, and I haven't found an example problem of this yet, I'll be honest. So we're not going to worry about it just yet until I figure out where it fits. But Kp is partial, P stands for partial pressure. So there's another expression we can write if you have all gases. You can write it in terms of the pressures of those things. Because a lot of times with gases, we can tell how many there are of something if we know the pressure and volume of stuff, which is gas laws and that whole thing. But there's different symbols here is what I'm getting at. So it's still products over reactants, but we just say like the partial pressure of gas C, and then how many of that thing. Notice I'm doing parentheses now. Parentheses is for pressure. Concentration gets brackets. Product or the partial pressure of gas D. Ooh, I should use capital there. Capital D. And then how many of that you've got the partial pressure of gas A times the partial pressure of gas B. So if it's asking for a Kp value instead, know that you're plugging in pressures here. And the expression would change to parentheses instead of brackets. We don't have one that's asking for that just yet, but that is technically a thing. So just keep that in mind. Okay, so if I go too fast at any point, just yell at me. Let me slow down. Okay, let's do a couple of examples, just like writing this out. Okay, so it says here, write an equilibrium expression for each of the following. So since it said equilibrium expression, I'm going to assume it's like K, Keq, or Kc. Like I'm going to write it in terms of the concentrations of things, it didn't say anything about Kp or anything with pressure. So I'm just going to assume I'm going to write it with brackets for everything. Okay, so remember, I'm only including gases or anything aqueous. So if I look at my reaction, the first thing I do is I just cross out anything that's not what I want. So right now I have I2 in this reaction, which is a solid. The concentration of a solid doesn't change. It's a solid thing. So, so it's not going anywhere. So, all right, I have K, EQ, I'll just put that for equilibrium expression. And then I'm going to do products over reactants. So I've got brackets. So my product side, I've got HI. So I would put, if I had a number, we're going to look at some numbers, but concentration of HI, and then I would square that number, whatever it is, if I were to get it, because there are 2 moles of that thing. So that's what the 2 becomes the exponent. And then I just do the other side, the reactant side. So that's going to be H2. And I only have one of those. There's no number out front. So you can put the one up top, but you don't have to. It's just if you want to stay consistent with your conventions, please feel free to do that. Otherwise, you do not have to put the 1. And that's the equilibrium expression. How do we feel about that? Freaked anyone out yet, other than myself? No. But I haven't done equilibrium in a good long while. That's not an SVG chem, so we did not do that. Okay, people at home, hopefully you're still there. We're just moving forward with the things. Okay, let's look at number 2. Which things, let's kind of do one together a little here. Which things are we going to cross out? So which things do I not want for my equilibrium expression? What are our thoughts? What am I going to start crossing out? What do I not want? Harley, what do you think? Oh, and Josie said something in the chat. What do you think? Yeah, this is a tricky one. Some people see the water right here and they're like, oh, look, maybe it's aqueous. Oh, no, this is a solid. This is a hydrated compound. So the compound itself in the structure of this has some water particles in it as well, like trapped, stuck with it. Can't get out. So that's a solid, though. We're going to take that one out. So don't get tripped up by any of the hydrates. This is another one we're going to take out. So the equilibrium expression on this one is really only reliant on this gas right here, because that's the thing that's going to kind of hop between the 2 sides, forwards and backwards, because it's a gas, and gases do that. So for this one, it's just going to be H2O, and then to the 5th power, and we don't put anything on the bottom because our reactant is just a solid, kind of sitting there, and every once in a while it lets off some water vapor, usually when you heat it. And then a little bit of that water vapor kind of travels back and reattaches itself, and then you've got to, so it's kind of bumping back and forth. So that water is the thing that water vapor is driving that backwards and forwards process. Okay, and then the last one. This does have all gases on it. I think unless the problem's asking you for KP specifically, that's when you would, or you have pressures given instead of concentrations, that's when you would use this notation. But they didn't ask for that here, so we're going to write it this way. These are all gases, so we are going to include all of these. So we've got our product, ammonia, NH3, mix of bleach, and then square that one. And then our 2 reactants. And N2 is not going to get an exponent because there's only 1. And then H2 going to be to the 3rd power. And that's that. That's just writing an expression. What questions do we have? Anything at all? Sorry for moving too slow. Just making sure we have everyone. Don't lose anybody. Okay. The only other thing I'm going to label here is if this is a homogeneous equilibrium expression or if it's heterogeneous. That depends on the state of the things. So if you notice here, We have a solid that's part of our equation, which didn't show up in our equilibrium expression. So this one I would say is heterogeneous. I'm gonna butcher this word, sorry. Same thing with this one. This one is what we would call homogeneous because it's all of the things got included and they were all the same state. So that's just, sometimes you'll hear an equilibrium expression referred to as heterogeneous or homogeneous. That's what they're talking about. So that way you know if everything's in the same state or not in the same state. Okay. Let's try some. I'm going to give you guys a couple minutes. Try to write these on your paper, people at home. The only one I'm going to give your attention to here is the KP one. This is the one where you're using parentheses instead of the brackets. And you don't have to write it on the Jamboard. You just write it on your paper, and then we'll have some people share, perhaps. That sounds good. Yes, Marley. KC just means concentration. KC and KEQ are kind of interchangeable, I believe. If that's incorrect, I'll fix it on Wednesday, but I'm pretty sure those generally mean the same thing. Equilibrium is the rates of the concentration. Like it's the rate over top and bottom products and reactants, which we always look at concentration for that. So these essentially are written the same way. Brackets dependent on concentration. Does anyone have A done that would like to tell me how to write it? Yeah, Thomas, what am I doing? Great, yeah. There's number one. People at home. Anyone at home want to volunteer? You want to unmute yourself? Tell me how to do it. We could do part B. Feel free to hit the raise hand button to volunteer. I love hearing people's voices. Virtual learning is so quiet. I mean, I'm an introvert by nature, but Marley, did you try B? Did you want to take a stab at it, or? All right. What's up? Pressure of anode in wall. Yeah, and eventually we would put numbers in, like we'd be given numbers. We're gonna eventually calculate stuff. All right, do I have anybody for part C, part C in the room or at home, feel free to hit the raise hand button at home. You can tell me what to write for part C. Don't get too excited. Try to keep it together out there. Anyone in here want to try part C? Tell me what to write. Riveting content, I know. Harley, do you want to tell me what to write? You keep staring at me, so we're doing it. Anything on the bottom? Why nothing on the bottom? This is a solid. Get rid of that guy. Don't want it. Okay. Any questions about these three before we bop on along? People at home, drop it in the chat. Morgan's good. Thank you. Hello. Okay. All right, so scientists eventually, we plug numbers into this stuff. So it's not just like you just write all these expressions for the fun of it. We actually will put in, different concentration values. Sometimes I already know the ratio and I'm trying to backtrack and solve for one of the other things. Same thing with the pressures if they're asking for pressure amounts instead of concentrations. But basically you end up with a number. I mean, K is going to be some sort of number. You're going to multiply the stuff, divide the stuff. You're going to get a number. So scientists have to know what to do with the number. Chemists have to know what to do with it or interpret it. So we have to make sure we can interpret the number correctly as well. So if K is 1, then that means you have an equal ratio of products and reactants. So sometimes at equilibrium, everything's happening at an equal rate forwards and backwards, which doesn't always guarantee the same amount of things, just the rate is the same. But there are certain reactions where there's an equal ratio of those pieces and parts as well. If K is bigger than 1, so if you think mathematically, we get a number here that's bigger than 1, that means there's more products. So you've got the products are favored or products are greater than the reactants at equilibrium. So if you were looking at a graph, oh boy, let's see if I can do this, of a reaction that was favoring the products at equilibrium, this would be that graph. So these are all kind of work together. You can put all the pieces and parts together. If K is bigger than 1, you're favoring the products, so there's more products than reactants, and this is what the graph would look like. You'd have something like that. If it's less than 1, that means like the bottom number is bigger when we divide. So a little bit of math there. So we have more reactants than products. So the reactants are favored. So you would have a graph. You'd have a graph like this. I gotta think. Sorry. Ooh, product. So you'd have a graph like that. The reactants, you'd still have more. So what we have to do sometimes, or what you'll have to do is they'll give you the K value and you have to talk about which thing is favored. So you just have to remember it's products divided by reactants. So thinking about which number is bigger and then which one is favored. So let's try a couple. Did everybody have that? Sorry, I get excited sometimes. Okay, again, this is recorded for your viewing pleasure. All right, so let's just practice interpreting. So for these different constants, let's hypothetically say these came from some reactions. We plugged in numbers to our expression and got a value, actually. Which ones would have the products favored and which ones would have the reactants favored? So I'm going to do the first one, and then you guys kind of think of the second two. I'll leave the scientific notation for you guys. I'm kidding. Okay, this number, 0.25, is that less than 1 or greater than 1? People at home, feel free to drop it in the chat. Less than 1, greater than 1, 0.25. Marley's making symbols. Less than, always eats the bigger number. It's like, did you learn it the alligator way in elementary school? That's what I remember. And people at home are saying less, thank you. So this is less than 1. So we got to think back, okay, it's less than 1, which means the bottom number has to be bigger. mathematically. So here my reactants would be greater than the products. So my reactants are favored. So favored meaning you'd have more reactants at equilibrium than products. But the rates are happening at the same rate. Okay, this scientific notation number, what do we think? Greater than or less than 1? Emma, what do you think? Do you have any thoughts? It's Emma, right? Ooh, took a stab in the dark. All right, yep. Yeah, this is very much, I mean, 23rd power, this is very much greater than 1. So in this case, the top number, the product number has to be bigger than what we're dividing it by. So here the products will be favored. What about this guy? This little negative exponent, greater than, less than 1. People at home, drop it in the chat. Greater than or less than? What do we think? Greater or less than 1, that number. Feel free to drop it in the chat. What are you guys thinking here? Max, what do you think? Hello. I haven't seen you since Peru. I just been a hot second. Yeah. Hello again. Is it?
Oh wait, that's negative the other way.
Yeah, negatives to, yeah, negatives to the left. So this is right, 1, 2, 3, 4, 5, yeah. So that's gonna be way less. That's less than 1. So this one we'd have the reactants favored. Just meaning there would be more of them at equilibrium. What questions do we have, friends? Favored. You're gonna get used to my terrible handwriting. Sorry. Somebody's gotta buy me an Apple Pencil. They're expensive and I'm cheap. This is a $20 Amazon stylus. Questions on this part. How do we feel? Give me like a thumbs up if you're feeling okay, or a thumbs down. People at home, let me know how you're doing. How do we feel? Good, bad? Questions? We do have a thumbs up. We have a good. Okay. Hey, I haven't scared anybody off yet. All right. Okay, let's do some math. All right, this is okay. This is fine. This is easy math. Okay, you may want a calculator though. People in here, if you want to not use the one on a Chromebook or your phone, there are some back there that are sanitized. But okay, let's do one with math. So let's actually like put all the parts together now. Let's get a K value for something and decide what the reaction is doing. Because like, I mean, chemists again don't just write random expressions and not do anything with them. That wouldn't be any fun. Okay, so we're gonna start here with this question. It says calculate the equilibrium constant. So that's K, EQ, Kc. They ask for Kp, it would be given in pressures, but we have M for molarity here. So they're giving us some concentrations of each of our things. And the ultimate question here is what is favored? So we're going to have to do this in a couple steps. We'll have to write our expression, plug in the numbers, and then evaluate if the number is greater than or less than 1 or equal to 1, figure out what that means. So who would like to help me? I'll take a volunteer. Don't all jump at once. Either someone at home you can talk me through it or somebody in the room. I got to write my expression first, my equilibrium just in general with my symbols. So who would like to do that part for us? Don't all jump at once. I don't know what time this class gets over. Is it soon? Great. Okay. We got time then. Okay. Marley, we made eye contact. Great. Tell me what to write for this expression. What do we got? Yeah, I'm gonna put the symbols first in case anyone gets confused and plug in stuff. Okay, but what would my other part be on top? CL2. Okay, what about the bottom? Okay, these are all, why did we include all of those, Marley? Why did I include all 3 things? Yeah, no solids or liquids here, so we're gonna include everybody. Everybody gets a shot. Okay, and then like Marley started jumping ahead, we're gonna put in our numbers for each of these things. I'm gonna put parentheses, I guess. So we're gonna plug in on the calculator. Nope, not that number. What are you doing, Fitz? Okay, we've got so these two on top, so we've got 0.25 times the same 0.25 divided by 0.15, and we want to get a number. So people at home, if you've calculated, drop it in the chat. People in here, you can say it out loud. Anybody get a number for anything? I just want to plug and chug. I'll hop on the train. Harley, did you get a number? Did you not get a number yet? 0.4167, or 0.42. I don't know what the rounding rules are at AP Chem. Are you allowed to round? Oh, thank you, Josie. You're allowed to round? I don't know either. Okay, stats you can round as long as you round correctly. So I'm gonna assume that's that. Okay, so that's our equilibrium value. So at equilibrium, this is the ratio of reactants to products and how quickly those are happening backwards and forwards. So which one is favored? Thomas, is this bigger than 1 or less, or not? Less than 1? Yeah, it's less than 1. So 0.4167 is less than 1. So that means for our ratio, products would be less than the reactants. If we're getting divide and get something less than 1. Products are less than reactants. So the reactants are favored. So that's putting all the parts together. Yes, sir.
So for 0.42, what are the units for that?
Great question. I forgot to say that there are no units on this value. Thank you for asking that. That was on my sheet and I forgot to say it. Don't worry, I'm gonna go back and look at the sheet and make sure I said everything I was supposed to say. But yes, there's no units because we have concentration values for everything. So it's like the units just kind of cancel. It's like the top's in terms of concentration and the bottom is, so they cancel out like the units. So yeah, K does not have any units. It's just a ratio of your rates, which is based on your concentrations and all of that. So thank you for asking that. Yeah, no units on this one. Yep, you just put the number. That's it. You got your symbol here, but yeah, just the number. Any questions from people at home? I think we're 45, right? Okay. All right, so let me show you at least everything we've covered up to now. I figured we'd probably get into this on Wednesday. This is interesting. I don't know if it's hard or not. I mean, I remembered it sort of yesterday by some miracle, but we're gonna save manipulating K for Wednesday when we do a little bit of that. So what you'll want to practice, let me show you for tomorrow, and you can do this tomorrow or today. This is practice set 1. I also put on here the sheet from Friday because this answer key right here has all of the questions. So what I am more or less concerned about, and you can do this one of 2 ways. So if you have me for stats, I'm not about to sit and wait until you do your homework at 8 p.m. And try to grade your work. So I post the key. So you should try the problems on here if you want to try them on your own piece of paper. You want to keep a digital copy. That is up to you. But whatever you do try, just go ahead and double check with the key and make corrections to it. So as far as this sheet, obviously do the stuff from Friday. I think you got couple questions, like 2 questions assigned from that. And then we have done, I'm trying to see, yeah, we've done everything up to question 7. So you guys need to do 1 through 6 and double check those with the key before Wednesday. And then all I'm interested in is that you have tried it and you have corrected it. So I'm not looking for perfection on any of the questions by any stretch first time. So Wednesday, we'll start with questions about the practice problems, and then we can go over those, or if you want me to explain those more in depth on Wednesday, I should be able to. I've learned practice set 1. So Great. Yes, Marley, what's your question?
So, on Zoom for now.
Yeah, don't do practice set 2 yet. If you were here today, you got a hard copy of that, because I won't see you again, maybe. I don't know. I just got happy with the printer and I started printing stuff.
Sorry, not that big one.
I know. Yeah, you do not have to do problem set 2 yet. You haven't learned it yet, and neither have I. So, all right, Clarissa, what's your question? There's some questions on problem set 1. Yeah, don't do the manipulating ones. I mean, you can try it if you want. There is a helpful video posted in the Week at a Glance about that, but no, you do not have to do past 7. So just do up to through 6, 7, and 8. I'll kind of teach you on Wednesday. That's a little weird. Yep. Okay, great. That's it for today. So you guys can log off. Just try to 1 through 6 on practice set 1. And we will see everyone again on Wednesday for some math. Get excited.